Welcome to the Hadoop course from Eduonics. In today's lecture, we are looking at Introduction to Big Data and the first topic, why Hadoop, Big Data and MapReduce. Let's start with our core Hadoop syllabus. And today, we are in the first topic, Introduction to Big Data. And we are starting the first subtopic, why Hadoop, Big Data and MapReduce. In this topic, we will look at why you would want to use Hadoop, Big Data and MapReduce. We will introduce some of the terminology and concepts for Big Data at a high level, and then look at how Hadoop and MapReduce evolve the Big Data space from relational database technology. This document is called Why Hadoop, Big Data and MapReduce, and this document can be found in the directory for this subtopic. And this question, why Hadoop, Big Data and MapReduce? Why, as developers, would we be interested in these domains? And the answer is because it's a huge emerging space. Big data is an overarching term that can be used to refer to, obviously, a big set of data, but it can also be used to refer to a set of tools that you use to process that data. So this term can be a bit confusing and has different meanings depending on the context in which you use it. And so this will be the main focus for this subtopic, is to give a bit of understanding and clarity to the contexts and the meanings of big data in those contexts. We find a similar issue to a lesser extent in Hadoop. When people refer to Hadoop, they could be referring to the core Hadoop, which is a file system and a set of common algorithms that it implements, or they could be referring to the big ecosystem of Hadoop, all the tools that exist and use the Hadoop framework. So just like big data, it can have different meanings in different contexts. MapReduce is the algorithm. MapReduce is an algorithm that revolutionized big data. Now, we have moved on a bit just recently from MapReduce, but MapReduce was the key algorithm that opened up the big data space. Big data, and in particular the analysis of big data, is a very important emerging domain for developers and scientists and people that write code in general. And Hadoop, and in particular the MapReduce algorithm, are two new innovations in the big data space. And so the question, why Hadoop, Big Data and MapReduce? And one possible answer is because they work together really well. So big data has value, but it has a lot of issues and problems. So we can extract that value using tools like Hadoop and algorithms like MapReduce. So big data, Hadoop and MapReduce work together really well. Each technology deals with the extrinsic problems encountered when extracting value from the big data set. So when we want to try and extract value from big data, there are going to be issues. Firstly, it's the size of the data. Secondly, it's the structure of the data. And a third point, when we want to analyze the data, what will be the issues in using the tool that we need? We need a particular tool to access the data in a certain way so that we can perform the analysis with the tool that we need to extract that analysis. And so these issues can be solved with Hadoop and MapReduce, and that will be the focus of the entire Hadoop course, will be to illustrate how we can solve those issues centered around big data. Example technologies that we will look at. I'm assuming you are familiar with SQL, the structured query language, and relational databases in general. Relational databases such as MySQL, Oracle, SQL Server. I'm assuming you're familiar with these databases in SQL. I will only unpack in more detail the NoSQL and MapReduce in detail. For MapReduce we will look at Hadoop, and for NoSQL we will look at MongoDB. MongoDB is perhaps the best NoSQL database for a user and a beginner to look at first. Let's look at the types of big data. This table outlines the types of big data, and you can refer to it later if I go over any particular point too quickly. Structured data. The first type of big data is structured data, and we can describe this as data that is organized into entities. Now, entities can refer to any type of object. It's just a general word. A spoon or a cup or a table or a house or a car, all these things can be entities. An entity is just something. So structured data is data that's organized into entities that have a defined format. And another word for defined format can be schema. So data is organized into entities that have a defined format, such as XML documents or database tables, and a database table in a relational database. So a relational database has tables, and these tables conform to what we call a predefined schema. And that predefined schema is a defined format for the columns in the table, the data types, whether a column be a string, an integer, a date, or something else. Then, the preferred technology for structured data is the relational database or NoSQL. NoSQL is a database that's different to a relational database in the sense that it doesn't have predefined schemas, and it's often quite convenient to think of NoSQL databases as being object databases. Many NoSQL database builders, designers and distributors would argue against that definition for NoSQL. Rather, we're thinking of them as being document stores. So when we have structured data, the preferred technology is a relational database or a NoSQL database. Then we have this idea of semi-structured data. This is data that is looser. While there may be a schema that is a defined format, it can be ignored as it may be used only as a guide to the structure of the data. So a good example of this could be a CSV file where you have different numbers of entries in each row. Perhaps you've encountered having to process data like that. A CSV file, we have different numbers of comma or delimited tokens for each row. And the technology for dealing with semi-structured data is the MapReduce algorithm, which we will talk about later, or the NoSQL database. And then finally we have unstructured data. Unstructured data does not have any particular internal structure. It's not an XML document, it's not a CSV document, it's just a whole lot of different stuff. For example, plain text or image data. And the best technology for working with unstructured data by far, and essentially for any big unstructured data sets, and that's what we're talking about now, big data, is MapReduce. So for unstructured data, MapReduce. For slightly structured data, semi-structured data, MapReduce or NoSQL. But if the data is structured, then a relational database or NoSQL is best. Now we will illustrate the core concepts in each of our technologies, RDBMS, NoSQL and MapReduce, by looking at how they solve a simple problem. And that simple problem is to compute the average age for the people in each city. So looking at RDBMS. For RDBMS, we will use the structured query language SQL. Here is a database. The name of the database is people. And the people database has a table called city. And this is what that table might look like. This is a fragment from that table where we have a city ID, we have a person ID, and we have an age. So each person has a person ID, and they belong to a city with a city ID, and they have an age. And this is what the structured query language SQL query would look like. These are aggregating functions provided in SQL. And SQL has a group by clause which aggregates the results. So we select the city ID and average age of all the people for that city ID. We select from the database people, and we group our results by city ID. So this simple query shows the power of relational database systems with the structured query language for queries. Now we will look at our simple problem to compute the average age for the people in each city, how this would be solved in the MapReduce in Hadoop way. So for the MapReduce algorithm, we have three basic steps. We have the mapping step, the shuffle step, and the reduce step. And now we'll try and illustrate each step. Now recall, we have a city ID and we have an age for each person. So in the map step, we create these key value pairs. So if the city has ID 3 and a person in that city has age 5, we will create a key 3 and a value 5 for the age and 3 for the city ID. So let's look at another person in city 3. Here we have the same key but a different value. So our keys do not need to be unique, nor do our values need to be unique. And in the mapping step, we extract from the data, the unstructured data or semi-structured data, a key and value pair for each record or each data item in the data. So this is the map step, and in the actual design algorithm pattern for MapReduce, you can consider this the scatter set. Here we are taking the data and scattering it into a set of key value pairs. Now we look at the shuffle step. In the shuffle step, we simply sort by key. So now we are sorting the keys, and we are having this idea that each key will be unique now. So we aggregate the values for key 3. Two values for key 3 that have the values 5 and 7. So for now, for key 3, I make a list of values 5 and 7. So this is the shuffle step where we sort by key. So we aggregate to unique keys and collect the values for each key. Then the final step is the reduce step, and you can think of this as gathering the data together. So now, because we're working for the average, we take the average for the values for each unique key. So we can think of one row in this map step table as a mapper, and we can think of each row in the reduce step as a reducer, and then we aggregate our final results. So this is the MapReduce approach to our simple problem. And now finally we'll look at our simple problem to compute the average age of the people in each city in a NoSQL technology. And the NoSQL technology we will illustrate is the MongoDB database, which is a very simple and easy to get started with database, even though its syntax may be a bit daunting at first. To actually set MongoDB up and to work with MongoDB is actually very user-friendly. So here we have an example dataset object. Now in MongoDB, data is stored as a JSON object. JSON stands for JavaScript Object Notation, so by default a JSON object is also a JavaScript object. So you can think of MongoDB as being an object database for JavaScript objects, or a document database for JSON documents. So here we have a city, and the city has an ID, and the city has a population. So the aggregation framework, so MongoDB has an aggregation framework, so we would write an aggregation function for the set of objects of this form in the NoSQL database. So in MongoDB we don't have tables, we have this idea of a collection of objects, and we have aggregation functions that will work on these collections. So here we are doing group steps like in the SQL query. So here we are grouping by state and city the population, and in this function for each city we're summing the population, and then now we're aggregating to state and we are averaging the city population. This function aggregates and works out an average of the population, and then we're sorting by that population, and we're sorting to unique results, and we're going to output a limit of 3 just for a simple illustration of the data. So this is the actual MongoDB aggregation framework language where you would use to solve a simple problem. And so the key points here, or the core concepts here, are that MongoDB stores JavaScript objects, or equivalently JSON documents, that are basically key value pairs. And MongoDB has an aggregation framework where, like SQL, it has inbuilt functions that you can call. So it has a summation function and an average function, and you can group and sort. Very similar in a way to an amalgamation of the SQL and the MapReduce. The aggregation framework for the MongoDB database I highly recommend as a very useful and easy to get started with technology. Once you work with it, the syntax becomes clearer. Now we've illustrated each technology by looking at how you would use it to solve this problem, computing the average age for the people in each city. So let's just quickly summarize the results. Firstly, for the RDBMS, we have a strict format for the data called a schema, and the data must strictly adhere to this schema. This results in a clear and simple query. This query is clear and simple because the data is so highly structured in a strict format. For MapReduce, there is no real structure or schema, but we're free to choose how we will map from the data to key value pairs, which we send down a pipe in a shuffle step and finally aggregate in a reduce step. In NoSQL, we have an object store where we're free to store what objects we like in a collection. And then we have an aggregation framework for the database where we have aggregating functions built in to the database that we can call in a query language that's not as clear and simple as SQL, but provides a powerful framework that I highly recommend. Let's quickly go through the key points as it relates to each technology. Let's start with MapReduce. Firstly, all the steps in MapReduce run in parallel. For any map step, for any mapper, for any reducer, or any shuffle step between a mapper and a reducer, we run in parallel, and they are independent of each step. MapReduce is a good fit for processes that need to analyze the whole data set, and generally we use MapReduce for big data sets in one batch operation, and then we analyze the data at the end using a range of tools. MapReduce interprets the data at processing time. What we mean here are the input keys and values for the data are not an intrinsic property of the data, but rather are chosen by the person writing the MapReduce job and analysing the data. MapReduce scales in a linear way, so as the data set increases, the actual time only increases in a linear way. A developer's task is to write map functions and reducer functions that pipe through a shuffle sort. MapReduce defines a mapping from one set of key-value pairs in the map step to another set of key-value pairs in the reduce step. And these steps do not care about the size of the data or the size of a cluster they are operating on, so they can be used unchanged for any data set, small or large. Now we will summarize RDBMS. RDBMS is good for queries or updates where the data set has been indexed, and this allows for low latency in retrieving data and low latency in update times of a relative small amount of data. Where MapReduce suits application, where the data is written once and read many times, the advantage of a relational database is that it's good when the data set needs to be continually updated and continually read. Relational data is often normalized to retain its integrity and remove redundancy. Now let's summarize NoSQL. For the 32-bit MongoDB distribution, we can only use 2 GB of data. Sometimes NoSQL has restrictions that we wouldn't encounter for a MapReduce implementation. But these same restrictions would apply for RDBMS. MongoDB has a 12-node limit to any cluster size. So when I run MongoDB on a cluster, I can only have 12 nodes. This can lead to disk space issues. As the database grows, I could run out of disk space and be unable to create other nodes to accommodate the increasing need for space to contain data. In MongoDB, a database is composed of collections which are like tables in a relational database. A collection contains documents which are JSON objects. JSON stands for JavaScript Object Notation, so I can think of a JSON object as a JavaScript object, so I can think of MongoDB as an object database. Queries are performed on a single collection. There is no equivalent of the SQL join, where I can join many tables together to write one query that accesses the data in different tables at the same time. This means that when I create a collection object, I need to denormalize. That is, in the collection object, I need to include all the fields I would need in any query. This can be a significant disadvantage over time. However, MongoDB doesn't enforce a model or schema, so in any one collection I can store any type of object I like. This can be good, but can be bad if over time you forget what objects you have in a collection. Mongo allows optional fields. It doesn't enforce a strict schema. Where SQL, the schema is very strict and every field is predefined. As per Mongo 2.2, there is a per database log, which means that operations on any database with the same collection can't be done concurrently. MongoDB operations are only atomic on the document level. These logs in traditional databases are used to guard index access, are only held as long as a single document takes to update in memory. So once a document's in memory, then you're free to write to the collection that the document came from. But while the document is being loaded into memory, that collection is locked for any other threads that want to update or access that collection. This can cause problems in a parallel multi-threaded environment. Let's tabulate our results for easy analysis. Now, first we will look at data size. RDBMS and NoSQL successfully deal with very large data sets of gigabytes of data, but MapReduce scales for its distributed parallel architecture to petabyte data sets. For the largest data sets, we use MapReduce. For access to the data, RDBMS and NoSQL offer interactive read and write queries and batch, whereas MapReduce is much more a batch system. For updates, where we read and write to the data, for RDBMS and NoSQL, we can read and write many times, where MapReduce, because of its highly distributed nature, is much more a write once and read many times. We can think of this in a way that for MapReduce systems, writing is expensive, but reading is cheap. Now, traditional RDBMS systems offer the fastest read and write. One place where you can find RDBMS systems scaled to massive data sets and used very effectively is in the telecommunications industry with a technology known as MySQL cluster. However, NoSQL data systems have come to the fore because RDBMS systems, when we join tables, are much slower than a NoSQL system where we have a correctly denormalized schema. Now, the structure or the schema. RDBMS have the most strict schema requirements. There is no concept of optional fields, and any one data store or table must have the correct number of fields, and the schema is static. It cannot be changed. We find precisely the opposite situation in NoSQL, where we can think of NoSQL as an object store. In NoSQL, we can create different types of objects and store them successfully in the same store. This can lead to problems with organization of the data. Whereas MapReduce, we are free to create whatever schema we want from the data set. RDBMS and NoSQL are designed for high integrity of the data, whereas MapReduce, because we run it on commodity hardware, is designed so that parts of the system can go down, but this does not affect the integrity of the data. RDBMS and NoSQL, because of their higher structural requirements, scale in a non-linear fashion. This means as the data sets increase, we need to increase our resources in a non-linear way. We find the opposite in MapReduce. As an advantage of its parallel system, we can just plug in cheaper nodes to increase our capacity to scale the data. Hence, MapReduce scales in a linear way. Why the Hadoop ecosystem? Now, as I mentioned before, when traditional RDBMS systems are used in big data, they are used in clustered system. One example of such RDBMS technology is MySQL technology, MySQL clustering technology. Now, for highly structured data, I can deal with extremely large data sets and have very effective read and write times, and this is exploited by mobile technology, mobile phone telecommunications companies. Now, when we have Hadoop and MapReduce, we run a batch job, a MapReduce batch job, and our data is distributed across many nodes in our cluster, and so our read and write is limited. So our data analysis of our batch results is limited. Enter the Hadoop ecosystem. This is why we have the Hadoop ecosystem, so we can process and run queries just like a traditional RDBMS system. So the Hadoop ecosystem consists of, firstly, the core common components of Hadoop, a set of operations and interfaces for the distributed file systems and getting the data in and out in streams, Java remote procedure call, and persistent Java structures with serialization. Then we have Arvo. It's a serialization system for efficient cross-language persistent data storage. than the MapReduce algorithm itself for running the batch job on large clusters. Then we have the HDFS file system, the Hadoop distributed file system that runs on large clusters on commodity low-cost machines. Then we have Pig, which we will look at later in the course, and this is a scripting language that allows us to explore and manipulate very large data sets in parallel. Pig runs very well on HDFS and MapReduce clusters. Pig is a scripting query language, a little bit like the NoSQL aggregation frameworks like we find in MongoDB. Whereas Hive is the equivalent for the RDBMS. Hive uses an SQL query language, and it's known as a distributed warehouse. Hive manages data stored in HDFS and provides batch-style computations by ETL functions, or extract, transform and load functions, and uses a HQL variant of SQL. Now we will write some ETL classes in Java to demonstrate ETL. Then HBase, possibly the best data store. It's a distributed column-orientated database. It is the Hadoop equivalent of Google BigTable. HBase uses HDFS for its underlying storage and supports batch style computations using MapReduce as well as queries. Scoop, very important, a tool for moving data efficiently between RDBMS and HDFS. A very important tool. And finally, for the up-and-coming, emerging, important field of machine learning, we have Mahout. So this is a quick discussion of the Hadoop ecosystem. And we have the Hadoop ecosystem so we can perform the same sort of data analysis that is possible in RDBMS and NoSQL for our MapReduce batch output. A final summary. RDBMS can scale effectively when used with a clustering technology like MySQL cluster, for example, frequently used by the big telecommunications companies. However, RDBMS requires a strict schema and a highly structured data set. When we join tables together, reads from such tables can be very expensive. NoSQL scales effectively. We saw for MongoDB, the best introductory NoSQL database, that there can be, in some contexts, architectural limitations that, for massive data sets, could be a bottleneck for capacity. NoSQL has elastic schemas and optional fields, and also no joins when the data structures have been correctly denormalized. MapReduce scales to, by far, the largest data set. It is possible to optimize writes, however, reads are slow. As the data set is distributed, we need to stream results somewhere or use the Hadoop ecosystem for queries.